So first this is the Boolean equation that given for the question and we need to simplify it. So first we need to apply the De Morgan theorem to break the bar, and then we simplify the each bracket, and then we use the absorption law where is the A plus AB equals to A, so the longer terms can be removed. Then the final expression is D bar plus AC bar. So then we explain it as D bracket A bar plus C bar. So this is the get level circle based on the simplified Boolean equation. So the just now the equation is D bracket A plus C bar. So the A plus C is all get, and then the combine together with which is the AND get for the simplified Boolean equation. So based on the simplified equation, we can generate the truth table. So when D equals to 0, the output X is equal to 1. So when the D equals to 1, the output is depends on A and C. If A equals to 0 and the C equals to 0, so the X is equal to 1. Otherwise, the X is 0. So this is the transition level CMOS design. First, we draw the MOS first. So the A plus C means A and C is drawing in parallel, and the D times A plus C. So it means the MOS D is in series. And then we draw the PMOS, which is opposite to the MOS design. So this slide shows the stick diagram of our CMOS circuit. So the yellow part we use is DCA, which means the transition gate are arranged in the order DCA, and the PMOS and the MOS must same for the gate order. So the PMOS is placed at the top and then connect to the VDD, and then the sequence is VDD to D, and then X, and then to C, and then the 1, and also the A, and the last is back to the VDD. And based on this sequence, and then we can draw the stick diagram, and also same with the MOS.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Nazam Binti Syari and my modus number is CE220135. Today I want to present about the transistor sizing. So as we can see from the slide, we have a pull down and pull up network, which is pull down is a NMOS and pull up is a PMOS. So for our transistor circuit, we have three input, which is A, C and D. So the width for NMOS is 4 lambda, and the width for PMOS is 8 lambda. So as we can see, the length of the both PMOS and CMOS is 2 lambda. So next we move to cadence simulation. As we can see, we already draw the CMOS inverter schematic in the cadence virtuos, also the transistor size in the schematic. So as we can see for NMOS and PMOS, we have a different value, which is for width in nanometer. So for NMOS, the value is 90 nanometer, and for PMOS 90 nanometer also, and for PMOS for input A is 180 nanometer, and for length in the cadence simulation we set as a 45 nanometer. We draw transistor level at cadence simulation. So this time we need to convert the transistor level to inverter symbol, which is this inverter we need to modify as a inverter level that we have drawn previously. So as we can see here, we have a three input, which is A, C and D, VSS, VDD, and also signal to output for this inverter. After we modified the inverter test band for transistor simulation, we got like this. This is a transistor test bench that we have already modified. So next is for result analysis and discussion. So after we modify our inverter, so this time we need to run the simulations to get the graph. Okay, as as we can see from this picture, this simulation run smoothly and there's no warning, but the graph cannot come out from the software. Lastly, after we check the home accounts for cds.log, we got a few error and we have tried many times to solve this part, but we failed to solve it, and we just only got the process level, CMOS logic gate, and inverter symbol and modified inverter for this project. And that's all for me, and thank you.